Hello class, today we'll be discussing the theory portion of the video for the Rydberg constant. The idea comes from, well, the idea is the following. We go back a little. The story begins with Johann Balmer. He was making measurements in the emission lines of a hydrogen in a discharge lamp. And so what he found after trial and error is that there's a relationship to describe the wavelengths of those emitted lines with respect to that follow this sort of relationship. So after trial and error, he found this formula to hold true for the emitted lines of hydrogen. Robert Rydberg. So this little r is now called as Rydberg's constant. He then generalized this formula. Rather than now you see here, this is 1 over 2 squared minus 1 over n squared. He took it further and said that it doesn't not only apply for 2, but you can have this relationship to be the way to describe the wavelengths of the emitted line of a gas in a discharge lamp of those excited atoms. You have 1 over nf squared, which is 1 minus 1 over ni squared, where n of I is greater than n of f. So what does these n's represent? What do they mean? Now we call them the principal quantum numbers, but they are used to represent quantized energy states. So is this just a coincidence as to why there's such a relationship, or where does it come from? So to talk a little bit about that, we need to consider the Bohr's model. So the Bohr's model stated that we have a compact nucleus that's positively charged, surrounded by electrons in stable orbits. So if those electrons live in those stable orbits, they do not radiate energy. Okay, now this orbits where they stay, they can also be called energy states. So for example, N1, N2, and N3. And the only way they can travel they can move from energy 1 state to energy 2 is by the absorption or emission of light. So if we use the Einstein's equation that we might recall from the photoelectric effect, and we keep in mind that this electron, as it's orbiting around the nucleus, it's under the presence of an electrostatic force. So we have this, you might remember from your electromagnetism class, that your electrostatic force is the charge squared divided by the radius, the distance between the two charges, times this proportion, 1 over 4 pi times epsilon 0. Now this electrostatic force is also, since the electron is orbiting, we also take into account the presence of a centripetal force. If we combine these two, I don't want to go through the third derivation, but if we combine these two, we obtain with the condition for stable orbits, which is that the angular momentum is equal to integral multiples of n times h over 2 pi. Now n, again, here means principal quantum numbers, so, and this could go to infinity, if theoretically speaking. So if we combine these three relationships, we get two expressions, one for the radius at each energy state, and a velocity at each energy state. Okay, so then we remember that we're talking here about total energy. So the total energy of an electron that is orbiting the nucleus, we say we need to consider the kinetic plus the potential energy, right? And from mechanics, we know that the kinetic energy is 1/2 mv n squared minus this potential, electrostatic potential energy, And it's a minus because we know it's attractive between the two, right? If we do the math, we combine the two expressions. We have kinetic and potential energy, and we get this expression from the result, right? And so we recall that the light emitted here, it's equivalent to the energy difference between the frequency or wavelength in this case. It's equivalent to the energy difference between the two energy states, N1 and N2, for example. And so we just use this expression with this one. We come up with this, guy. Here. And so we just simply make, now you can see that it closely resembles this expression here. And so all we have to do left is, okay, so we know that that's the difference in energy from the transition. And so now we recall that that wavelength is equivalent to the energy difference. So we say hc over the wavelength, lambda, it's equivalent to this expression. And then simply we solve for 1 over lambda. So in reality, this Rydberg's constant is equal to the mass of the electron, the charge of the electron to the 4th power, 8 times the epsilon 0 times the Planck's constant times the 0 of light. And currently this accepted value for R is 1.097 times 10 to the 7, 1 over meters. Okay? All right, so now we have an idea where this guy comes from and what's its physical meaning. So let's talk about a little bit about the experiment itself. So let me erase this. It's probably enough. So what we have in the experiment, how do we go about this? So what we have is, let's go back to, so we have this sort of thing. So this is our power, that's our spectrum. So I don't know, let's call it spectrum tube. And then let's say here we have hydrogen, it's a hydrogen lamp. And what this one is doing, power supply. What this one is doing is applying a discharge, which is gonna result in the emission of lines, as I previously mentioned. And so now the experiment is the following. The idea of the experiment is following. Recall from the single slit experiment, if we consider the following. So this light will be sent here into what we call a slit. We call it a grating, but it acts as a slit. And so what we send is all of this light through a small aperture, which is comparable to the wavelength. So this aperture, let's say A, is comparable to the wavelength of light. And if this light enters through here, it will diffract. And if we have here, for example, our screen, you'll remember that when this light of comparable wavelength to the opening of the slit, it passes through, you get some diffraction. Right? And if you were to plot it on the screen, you get something that's minima, maxima, right? So that was the case for the single slit, that was the case for monochromatic light. Now here we have a source with multi-wavelengths. So that means we have different colors of light, so different wavelengths enter the place, and we remember that the locations of maxima were given by this relation. So where we find bright spots is given by this, let me call it M to avoid confusion, M. M is what we call the diffraction order. And this and theta is the location of the maximum. So, like I said, now we have multiple wavelengths of light coming in, and so you get this sort of pattern that's similar to the diffraction pattern. Now, having multiple wavelengths coming in here, you're going to still see the superposition of all wavelengths, so you're going to see the light, so the total light. Now, from this equation, if we're moving from here, from the center to here, we realize that first we're not gonna, first from here, different wavelength means that it's got a different diffraction angle. So you're gonna see that as you move away from the center, you're gonna have different colors. So this is not just gonna be a single peak like this, it will be a combination of red and then blue, and then here perhaps we have green. So although you see the maximas more or less around the same place, the superposition of it, you have individual peaks with the monochromatic light of different wavelength, but they're offset because of their wavelength, as mandated for that equation. The first time, if you move from center to right, the first time you see this, that's what we call the first order diffraction. If you move further along this line, you'll see M is 2. So it's the same idea, but this is more prominent, and then this will be less visible. Okay, and so this is M0, then we call this M-1 and M-2. So you will be testing to see, in the experiment you will be looking for, in the experiment you will be looking for the locations at which this maxima, so that is where you look for where you find the lines of different colors. For example, where do you find along this line red, where do you find blue, where do you find green? You form that relation, and you want to find what we call here the Rydberg constant. I think that concludes the theory part of the experiment, so we'll move on to the experimental setup for the next video.